Throughout this course, we will focus on electrons because they are the most important subatomic particle for chemistry. Why are these most important? Electrons are on the outside of an atom. So if an atom is going to interact with something else, it's going to be those outside electrons that are going to be bumping up against each other, not the neutrons and protons in the center of the atom. So you can think about the neutrons and the protons as kind of being protected in the center. The electrons are what's going to interact, they're going to be exchanged, they're going to be bumping into each other. Now, before we get too much into the electrons, I want to get a little bit of background. And this might seem a little bit on left field, but it does come back. Electromagnetic radiation is essentially the type of radiation that is light. So this is not to be confused with nuclear radiation or those types of things. Electromagnetic radiation, we can look at a variety of different frequencies and wavelengths of radiation. Here we've got the visible light spectrum from about 400 to 700 nanometers, or 4 times 10 to the negative 7th to 7 times 10 to the negative 7th meters. And this is not as important as what happens if we look at the spectrum that's created by an element. If we look at the atomic spectrum of an element, such as this is hydrogen, hydrogen gas, when we pass electricity through it, produces light at these very specific wavelengths. Notice that it is black in between. There's no light being produced. So there's very specific wavelengths of light. So scientists wondered, why is that? Why are we getting these very specific spectra from elements? And it's really because each electron has a very specific energy. These correspond to what's called the principal quantum number for the electron. So you can think about the principal quantum number as being essentially how far that electron is from the nucleus. So if we've got our nucleus, an electron here might have a number of 1. Further out, quantum number of 2, and so on. 3, 4, 5 can have quite a number of different layers. But what's interesting about the electrons here is that the energy of these levels is quantized. So it can only have very specific values. So it can only be in the n equals 1 level or the n equals 2. It can't be anywhere in between. So electrons are going to only be at these levels. They can't have a 1.5 or some other intermediate value. This corresponds to what's called electron energy levels. So you can think about these as kind of like rungs on a ladder. These are a variety of different ways of depicting them. Essentially, these energy levels start from the bottom, energy level 1, 2, 3, 4, 5, and so on. And we'll look at how electrons are going to be built into and organized into our atoms, starting at the lowest energy level and building up. Within each of these energy levels, the electrons are arranged in sublevels. These determine the chemical and physical properties that we see of various elements. The sublevels are depicted by S, P, D, and F. We're going to be focusing on the S and P sublevels. S levels have the lowest energy, F to the highest. Here's another way of looking at them. This is the 1s level, 2s, 2p, notice that we have increasing amounts of energy. 3s, 3p, 4s. That's as far as we're going to go for this unit, but you can see that the subshells continue to build up. So you are going to be adding electrons to the atom from the bottom to the top. This is another way of looking at the orbital. This is the s orbital. Notice it's just, essentially a sphere. There's only one s orbital per energy level. Each of these can hold 2 electrons, so at the 1s level you can have 2 electrons, 2s can have 2, 3s can have 2. Notice that it gets bigger as the energy, as the quantum number increases. So the quantum number is that 1 or 2 or 3 here. p orbitals start at n equals 2. There's 3 different possibilities for p orbitals. It's not too important the exact shapes here, but each of these p orbitals could hold 2 electrons. But since there's 3 different options, at the p level you can have electrons in each of these suborbitals. So the p orbitals can hold a total of 6 electrons. Some folks are sometimes curious about why we can only have 2 electrons in each of those suborbitals. It has to do with electron spin. You can have only 2 different possibilities for electron spin in each of these sublevels. If we then connect this back to the periodic table, and this will look a little bit more as we make the configurations, is S or S blocks are here and here, P block here, D, and F block. We'll look at how we apply that and how that works when we actually create our electron configurations.